Welcome to another video. In this video, we are going to discuss some important conclusion from fluid dynamics while reviewing past paper questions alongside. In this video, we are going to cover Stokes Law, terminal velocity, continuity equation, and Bernoulli's principle, as well as turbulent and streamline flow. Let's get started. Um, First of all, know that there are two important types of flows. First one, we have a streamline flow, and then we have turbulent flow. In a streamline flow, there are imaginary lines that are called streamlines, and these streamlines are said to never cross each other. What happens in a streamline flow is if a particle A is at a point P1 and it follows the trajectory and goes to another point P2. Then, if the flow is a streamline, then another particle, let's say B, which reaches the same point P1, is bound to follow the same path leading to the same point P2. If so, then such a flow is called a streamline flow. Otherwise, the flow is called turbulent flow, where you cannot predict the trajectory of particle. The particle is not bound to follow the exact same path followed by the previous particle at any of the given point. And there is no such thing as normal flow. When it comes to ideal flow, a liquid is said to be a fluid in general is said to be ideal if it follows three basic conditions, like all three of them. First, if the flow is a streamline, it gives a steady flow. Also, if the fluid is incompressible, that is its density remains the same during the flow. And also, if the fluid is non-viscous, that is the internal friction between the layer of fluid, if is considered to be zero, then the liquid is termed as non-viscous. Such a liquid or such a fluid in general that follows all three conditions is said to be an ideal fluid. Now let's just answer this MCQ here. It says if each particle of a fluid passing through a point follows the same path, then the flow is called, of course, streamline flow. Now, fluid dynamics basically is governed by two most important equations. We have Bernoulli's equation and then we have continuity equation. Let's just consider a real life example. Suppose you are watering the grass, right, using a water pipe. And if somehow you block a certain area of the outlet, maybe by placing your thumb at this outlet, what happens? Speed of the fluid increases at the outlet, right? That is, we can say that lesser the area, greater will be the speed of fluid. That is, area and velocity at a certain point are inversely related to each other. This same is the consequence of continuity equation. Though it does not start from the same point, शुरू कहाँ से होती है ये? The equation suggests कि किसी एक टाइम पर जितना फ्लूइड का मास एंटर करेगा एक पॉइंट पे, the mass of the fluid leaving from the other point in the given time should exactly be the same. So we start from this point that m1 equals m2. Let's just say that m1 was the mass of fluid that entered in some given time interval delta t at this point, and m2 is the one leaving in the same time period from this point. Now we can always replace mass in terms of product of density and volume. Let's just write ρ1 v1, and here we can write ρ2 v2. And we can always replace this volume in terms of area and distance. In terms of area A2 and distance D2 for the second point. Now we know that this distance or displacement is nothing but rate of change of velocity. So we can now rewrite this equation as ρ1 A1 V1 delta t, and then same goes here. We have ρ2 V2 A2 and delta t, right? This delta t gets cancelled with this delta t because we are considering equal time interval. And since we are dealing with the ideal fluid, that means it is incompressible, that is its density remains constant. So the density of fluid at point 1 must equal the density of the fluid at point 2. This makes us cancel these two values and we end up getting this A1 V1 equals A2 V2. That is, the continuity equation says that the product of area and velocity remains constant. At point 1, their product leads to a specific value. This value shall remain same at any other point during the flow of liquid. Now that we have seen what is actually continuity equation, we should be able to answer this question. It says according to the equation of continuity, if the cross-sectional area of pipe decreases, then the speed of fluid passing through it increases. Because whenever the product of two values remains constant, so we say कि अगर कोई एक value बढ़ेगी तो the other must decrease to keep the product constant. Now, what will be the velocity of water falling from a height as it reaches the ground? We know that whenever we are dealing with the free fall motion, the speed of the object at the start of the journey is zero and it keeps on increasing due to gravitational acceleration. Like every 1 second, the velocity increases by 9.8 meters per second square. And we say that the velocity of the object is maximum just before hitting the ground. So this makes us conclude that the speed keeps on increasing. It says the equation A1 V1 equals A2 V2, where this A clearly is the area and V is the velocity of fluid, is valid for a fluid having what? In this chapter, Stokes law के अलावा जितने भी टॉपिक्स हम डिस्कस करेंगे we are going to study those topics with the assumption that we are dealing with the ideal fluid. And I just mentioned that ideal fluid is the one which follows three basic conditions. It is incompressible and it gives steady flow, right? So this makes us conclude that option B needs to be the correct option to this MC. The second most important equation in fluid dynamics is Bernoulli's theorem. This theorem actually relates the pressure, gravitational potential energy, as well as the kinetic energy. That is the total mechanical energy of a fluid at certain points. And it says that the mechanical energy remains constant. This is the reason Bernoulli's equation is also known as conservation of energy. This equation goes like pressure plus gravitational potential energy plus kinetic energy at a certain point remains constant. In different scenarios, at a point, we will consider two variables at a time. Either we'll ignore height or velocity by considering कि इस specific case में height change नहीं हो रही क्योंकि शायद हम सेम डेप्थ पर बात कर रहे हैं या हो सकता है वेलोसिटी चेंज नहीं हो रही क्योंकि हमने एरिया को चेंज नहीं किया. एट अ टाइम वी आर गोइंग टू डिस्कस इन तीनों में से कोई भी दो वेरिएबल्स और तीसरे को हम इग्नोर कर देंगे, राइट? एंड व्हेन वी से मल्टीपल फिजिकल क्वांटिटीज हैं जिसका सम हमारे पास कांस्टेंट आ रहा है, राइट? एंड इफ आई टेल यू कि फॉर सपोज हाइट इन दिस केस इज इंक्रीजिंग, बताएं प्रेशर का क्या ट्रेंड होगा? तो आप कहेंगे अगर हाइट इंक्रीज हो रही है लेकिन उसके बावजूद भी इन दोनों का सम कांस्टेंट है तो इट इज ओनली पॉसिबल अगर प्रेशर डिक्रीज हो रहा है. इन अदर वर्ड्स वी कैन से कि अगर आप इन तीनों में से वेलोसिटी, हाइट एंड प्रेशर किसी भी एक चीज को, किसी भी एक वेरिएबल को इंक्रीज करेंगे तो द अदर मस्ट डिक्रीज टू कीप द सम कांस्टेंट as suggested by Bernoulli's theorem. Now, let's just see what the question exactly asks of you. It says, which of the following statement is correct in light of Bernoulli's theorem? Speed of fluid is low at low pressure? No. अगर speed low हो रही है और आप इसे pressure से relate कर रहे हैं, यानी इस केस में आप height को ignore कर रहे हैं, depth constant consider कर रहे हैं, तो फिर हमें पता है these two should be inversely related to each other. Speed of fluid is high at low pressure. Pressure of fluid is independent of its speed? No, it is not, because we just saw an equation which relates कि pressure और velocity का आपस में क्या relation है. Theorem is valid only for turbulent flow of liquid? No, I just mentioned कि Bernoulli और कंटिन्यूटी इक्वेशन, ये सारे आइडियल फ्लूइड के लिए एप्लीकेबल है। एंड आइडियल फ्लूइड इज द वन जो स्ट्रीमलाइन फ्लो पर बेस करता है। Then, when an airplane is flying, the air moves from the top and the bottom of the wings. Air moves over the top of the wing. Air moving over the top of the wing is faster, due to which the pressure above the wing will be. See, the moment they said that the air moving is faster, that is, the velocity is greater, and they are asking you to relate this increase in velocity with the change in pressure. So as suggested by Bernoulli's equation, agar velocity increase ho rahi hai, तो it is only natural that the pressure must be low. Then the pressure in the upper region of an airfoil, where streamlines are closer to each other, results. In order to answer this MCQ, let's just see this figure right here, right? So from continuity equation we have concluded कि अगर area greater है इस region में, तो यकीनन यहाँ पर velocity smaller होगी, right? And this makes us conclude कि अगर इस point पे velocity smaller है, तो फिर यकीनन इस point पे जहाँ पर the opening is quite narrow, यकीनन velocity of the fluid will be greater. Did you see here? जब मैं कह रही हूँ velocity is smaller, तब these streamlines are farther from each other, right? And in the region where we are seeing that the velocity is greater, these streamlines are closer to each other. That is, in fluid dynamics, जब हम streamlines को present करते हैं, तो greater velocity is always represented by closer streamlines. राइट अगर किसी रीजन में स्ट्रीमलाइंस आर क्लोजर टू ईच अदर तो we'd say कि यकीनन इस रीजन में फ्लूइड की वेलोसिटी विल बी ग्रेटर एंड वाइस वर्सा. Now let's move back to the question. The pressure in the upper region of an airfoil where streamlines are close to each other result in, अगर streamlines closer हैं तो बताएं स्पीड पर आप कैसे कमेंट करेंगे? हाई स्पीड. I'm sure you can answer this one. Which of the following options represent the condition of an ideal fluid? A fluid which is non-viscous, a fluid whose density is constant, that is an incompressible fluid, and a fluid which has no internal frictional force, that is a non-viscous fluid, right? So 1, 2, and 4. Option D needs to be a correct option here. यहाँ पर इन्होंने fluid moving with high speed को mention किया है. A fluid moving with high speed leads to the turbulence, right? Turbulent flow आ जाता है वहां पर, और हमें पता है कि आइडियल फ्लूइड की तो कंडीशन ही स्ट्रीमलाइन मोशन होना चाहिए. So there is no way this option 3 could be the correct option for ideal fluid. Then which of the following designs is used in the given diagram? It is quite obvious that it is streamline. Then, at which of the following cross-sectional areas is the water flow fastest in the below region? See, you are to relate the area with the velocity. And कौन सी equation है जो इन दोनों को relate करती है? It is continuity equation which says the product of area and velocity remains constant. So अगर आपसे पूछा है fastest किस region में होगा liquid का flow, fluid का flow, तो आप कहेंगे यकीनन उस region में जहाँ area सबसे कम है. And it is quite obvious from this figure that A2 is the area which is narrow in all three of them. So you'd say that option B needs to be the correct option here. Then in which of the following sections of the given pipes will water flow with highest speed and lowest pressure? Highest speed सबसे ज्यादा तब होगी जब area सबसे कम होगा. What do you think? Option B needs to be the correct option. Which of the following options shows the correct sequence of lead in the increasing order of viscosity? It is obvious कि toothpaste और honey के मुकाबले में water is less viscous. हम कब कहते हैं किसी liquid की viscosity ज्यादा है? जब वो ज्यादा resistance show करे in its flow, right? So of course water is less viscous. It makes us exclude option C and D, and it makes us conclude that option A needs to be the correct option here because clearly honey is more viscous than paint. Which of the following is used to obtain a smooth motion? See, smooth regular motion is the result of a streamline because upthrust, turbulent or ripples in सबसे आपको एक irregular motion मिलता है, which of course cannot be the correct option here. Then Which of the following is not obeyed by an ideal fluid? I just mentioned in the beginning of this lecture कि Bernoulli और continuity equation, उसके अलावा Venturi tube, airfoil, atomizer, इन सब की जब भी हम बात करेंगे हम ideal fluid से डील करें. Like Stokes Law के अलावा इस टॉपिक में हम जितने भी एप्लीकेशंस की बात करेंगे वो सब इस assumption पे बेस्ड हैं कि हम आइडियल फ्लूइड को कंसिडर करें. So in this case, option A, that is the Stokes law, needs to be the correct option. Now, the fluid is incompressible, non-viscous, and it gives a steady flow. All of the following are based on the above conditions except, see, you can answer this question इस प्रीवियस वाले के ही बेसिस पे. स्टोक्स लॉ इज द वन जिसमें फ्लूइड को ये तीन कंडीशंस फॉलो करने की जरूरत नहीं है. बाकी व्हेन इट कम्स टू टॉरिचली थ्योरम, बर्नौलीज थ्योरम, इक्वेशन ऑफ कंटिन्यूटी, we are dealing with ideal fluid which is incompressible, which is non-viscous, and which flows steady. At which cross-sectional area of the given pipe water flow is fastest? Area and velocity are inversely related, so flow would be the fastest at the region which is narrower, which in this case is option B, that is region 2. In a cement factory, a viscous liquid flows through a pipe with an area of cross section 6 meters square at a velocity of 8 meters per second. Like at one point, this is the area and this is velocity. When this fluid moves forward, the area of cross section of the pipe decreases. This makes us conclude कि अगर area decrease हो गया तो यकीनन velocity increase हुई होगी, right? And they are asking you to evaluate this velocity at that point. So we are going to use continuity equation, that is the product of area and velocity shall remain constant. Now, let's just find this product at one point and we'll relate it to the one at the second point. Now, at one point, area is 6 meters square and velocity is 8. That is, the product gives us 48. So, this should remain same at the other point as well. That is, second point पे भी area or velocity का product should give you 48. And they've already mentioned कि second point पे area has reduced to 4 meters square. Now, what will be the velocity? All you have to do is just rewrite this equation so that this velocity becomes the subject of your equation. V equals 48 over 4, and this is nothing but 12, and since it is velocity it has to be in its standard unit of meters per second क्योंकि जो आपने already velocity place की थी it was in the unit of meters per second. So the correct answer here is option B, that is 12 meters per second. Bernoulli's equation is the fundamental equation in fluid dynamics that relates pressure of fluid to its speed and height. According to Bernoulli's equation, where the speed of fluid is high, the pressure will be low. It has already been established, right? क्योंकि इन सबका sum must remain constant. All of the following are the factors on which terminal velocity of a falling object depends, except you should be able to answer these two questions अगर आपको terminal velocity की equation याद हो, right? Because ये आपसे ये पूछ रहे हैं वो किस पर depend करती है या वो कौन सा factor है जिस पे वो depend नहीं करती है. टर्मिनल वेलोसिटी का कॉन्सेप्ट क्या था? वी स्टडीड अगर कोई ऑब्जेक्ट फ्री फॉल मोशन दे रहा है किसी फ्लूइड में, बी इट गैसियस मीडियम और अ लिक्विड मीडियम, तो एट द टाइम ऑफ रिलीज इस ऑब्जेक्ट की स्पीड जीरो है एंड स्पीड पर डायरेक्टली डिपेंड करती है ड्रैग फोर्स. तो अगर मैं कहती हूँ एट द टाइम ऑफ रिलीज इस ऑब्जेक्ट की स्पीड जीरो थी तो इसका मतलब है ड्रैग फोर्स एक्सपीरियंस्ड बाय दिस ऑब्जेक्ट वाज आल्सो जीरो, राइट? एंड एज इट कीप्स मूविंग डाउनवर्ड, ग्रेविटेशनल एक्सेलरेशन की वजह से इसकी स्पीड इंक्रीज होती जाएगी and consequently drag force भी increase होती जाएगी, right? There is already a downward force experienced by this object due to the weight of this object, right? Force of gravity, which equals the product of its mass and gravity. Downward move करते करते weight तो क्योंकि constant है, so the product of mass and gravity is constant. But drag would keep on increasing with the increase in velocity. And eventually, a time would reach where this upward drag experienced by this object will become equal to the downward force due to the gravity, right? And at this point, we'd say that the resultant force experienced by this object is zero because दोनों forces equal हैं और opposite direction में. और इस point पर हम कहेंगे कोई resultant force experience नहीं कर रहा ये object, इसीलिए कोई acceleration भी experience नहीं कर रहा. And when we say acceleration is zero, we mean कि change in velocity is zero. That is, object is moving with constant velocity, right? This constant velocity is termed as terminal velocity of the object, right? तो इसकी हम basic equation कहाँ से start करते हैं? हम कहते हैं terminal velocity के लिए basic condition क्या है? Force of gravity, that is weight of object, becomes equal to the drag force. How do we write force of gravity? It is product of mass and gravity. How do we write drag force? It is 6 pi eta rv by Stokes law, right? So we can rewrite this mass in terms of density. It would be density multiplied by volume, and क्योंकि we are considering a spherical object, तो spherical object का volume तो 4 by 3 pi r cube होता है, this g as it is, and the 6 pi eta rv as it is. इस कंडीशन में जब ये दोनों फोर्सेस इक्वल हैं, the velocity will be called terminal velocity. All you have to do is just rewrite this equation. This pi gets cancelled with this pi, and you can simplify these two, and you'd write rho r square, because this r gets cancelled with one of these r's, g over this eta, and this 3 into 3, that is 9. This is the expression for terminal velocity, right? Now you could see यहाँ पे आपसे कह रहे हैं it depends on mass. Of course it does not directly depend on mass, but it depends on density, right? And density is related to mass, we've seen here. So it depends on mass, it depends on gravity, it depends on density of the object, और इसके अलावा it depends on area, because r square is the dimension of area, ठीक? So here they are asking all of the following are the factors on which terminal velocity of a falling object depends, except it does not depend कि object की at the point velocity क्या है, right? It depends on कि object का mass क्या है, उसका cross sectional area क्या है, और gravitational acceleration क्या है. And kyunki we just solved terminal velocity, let's just answer this question first. When an object moves with terminal velocity, then its acceleration will be, अभी we have seen कि अगर कोई object अपनी terminal velocity को reach कर जाता है, तो this is the point जहाँ पर the force experienced by the object, net force, becomes zero, because इस point पे gravitational force drag force के बराबर है, right? And when we say the resultant force is zero, इसका मतलब है resultant acceleration भी zero हुआ, right? So its acceleration will be 0 meters per second square. If the different layers of a fluid offer no resistance over each other, then the fluid will be non-viscous fluid, because viscosity is the internal friction between the layers of fluid. In fluid dynamics, if every particle passing through a given point undergoes in an irregular pattern and fluctuation, then this type of flow is called turbulent flow, because the streamline flow was the exact opposite इसका, और तब हमने डिस्कस किया था कि turbulent flow कौन सा होता है, जिसमें आप उसके पाथ को ट्रेस नहीं कर सकते, आप उसके पाथ को प्रिडिक्ट नहीं कर सकते, जिसमें स्पीड बहुत ज्यादा हो जाती है फ्लूइड की, like it exceeds the critical velocity. In a firefighting machine, a jet is attached. By the way, jet is a nozzle which has a smaller area, right? A jet is attached to the head of a water pipe to increase the, जब मैंने mention किया कि jet का area कम है, तो यकीनन इसको लगाने से उस point पर liquid की या fluid की speed बढ़ जाएगी. So velocity of water flowing out of it increases. An industrial liquid flows through a section of pipe with an area of cross section 2 meters square at a velocity of 10 meters per second. यानी the product of area and velocity क्या आ रहा है उस certain point पर 2 into 10, which is 20. If at a certain section the area of cross section decreases to 1 meters square, यानी अब area reduce हो गया, तो it is obvious कि यकीनन velocity increase हो गई होगी, right? And we can already relate, area पहले के मुकाबले में half हो गया है, right? तो अब velocity पहले के मुकाबले में double हो जानी चाहिए. तो हम यहीं से भी प्रिडिक्ट कर सकते हैं कि अगर वेलोसिटी पहले 10 थी तो अब ये 20 हो जानी चाहिए. लेट्स जस्ट सी. अब हमारे पास एरिया है 1, वेलोसिटी कैलकुलेट करनी है, एंड एज पर द कंटिन्यूटी इक्वेशन द प्रोडक्ट शेल रिमेन सेम, राइट? सो we'll just rewrite this equation. It becomes 20 over 1, which is nothing but 20, and since it is velocity, it has to be in meters per second. According to Bernoulli's principle, when the pressure decreases during the flow of fluid through different sections of pipe, then the speed of fluid will increase, because Bernoulli's equation relates pressure, velocity and the height. इन्होंने height को mention नहीं किया, तो we'll presume के constant depth पे बात कर रहे हैं, यानी h1 और h2 की value same है. हम अपनी equation को reduce कर देंगे कहाँ पर, p1 plus half rho v1 square equals p2 plus half rho v2 square पे. So it makes us conclude that option A needs to be the correct option. Then let's just look at this last MCQ. The given diagram shows the same scale, vertical section of a set of circular vessels, each containing the same depth of water. Which of the following statement is correct? Like you can see in the options as well. आपसे पूछ रहे हैं कंटेनर के बेस पर प्रेशर कैसा होगा इन चारों में, कहाँ इक्वल होगा या किस केस में ज्यादा होगा या किस केस में कम होगा. In order to be able to answer this question, हमें पहले पता होना चाहिए किसी पॉइंट पर अगर हम प्रेशर निकालना चाहते हैं तो वो प्रेशर बेसिकली होता क्यों है, राइट, और ये किस पर डिपेंड करता है. अगर मैं कह रही हूँ इन केसेस में कंटेनर के बेस पर ये लिक्विड प्रेशर एक्सर्ट कर रहा है, तो दिस इज द प्रेशर ड्यू टू द वेट ऑफ द लिक्विड अबव द पॉइंट, राइट. यानी अगर मैं फाइंड आउट करना चाहती हूँ कि इस पॉइंट पर कितना प्रेशर है, राइट, तो दिस वुड डिपेंड ऑन द हाइट ऑफ लिक्विड अबव दिस पॉइंट, दैट इज इस हाइट पे डिपेंड करेगा. अगर मैं इस पॉइंट पर प्रेशर कैलकुलेट करना चाहती हूँ तो इट वुड डिपेंड ऑन द हाइट ऑफ लिक्विड अबव दिस पॉइंट, दैट इज इस पर डिपेंड करेगा. एंड अगर मैं डायरेक्टली बेस पर प्रेशर कैलकुलेट करना चाहती हूँ तो इट वुड बी डायरेक्टली रिलेटेड टू द हाइट ऑफ लिक्विड अबव द बेस, व्हिच इन दिस केस इज this one, right? Because pressure के लिए the formula we have is rho gh. The question arises, how did we get to this equation? Because we can write pressure as force per unit area, और यहाँ पर हम ये कह रहे हैं कि pressure is due to the weight of liquid, right? And weight को जब हम force के terms में लिखते हैं तो we can write it as the product of mass and gravity, this area as it is. Then we can rewrite this mass in terms of density as well. It is the product of density and volume. ठीक. और जब कभी मैं वॉल्यूम को लिख रही हूँ और मैं लिखना चाहती हूँ उसको एरिया के टर्म्स में, हाउ डू वी राइट वॉल्यूम? वी राइट वॉल्यूम एज द प्रोडक्ट ऑफ एरिया एंड हाइट. See, this area gets cancelled with this area. So the reduced equation for pressure in terms of density is rho gh, where this rho is the density of liquid, this g is the gravitational acceleration, and this h is not the height of container. It is the height of the liquid column above the point at which you are to calculate the pressure. And you can notice in all four containers here, the pressure which you are to calculate is at the base of the container, right? और आप देखें base से ऊपर the height of liquid column is same for all four cases, right? तो जब हाइट सेम है तो अंदर जो लिक्विड है वो तो ऑलरेडी सेम है, बिकॉज इन्होंने मेंशन नहीं किया कि वो अलग है. ग्रेविटी इज ऑलरेडी टेकन टू बी कांस्टेंट 9.8 मीटर्स पर सेकंड स्क्वायर. सो वी से कि इन सारे केसेस में सेम प्रेशर इज एक्सर्टेड बाय द वाटर ऑन द बेस ऑफ each vessel. See, water exerts same pressure on the base of each vessel.